Okay, so we're back again. This is going to be very easy for some of you who've done a fair amount of statistics. So, I mean, some things might be a little bit new, there might be some proofs that are a bit new, but anyway, so yeah. We're going to do very basic things, you know, Bayes rule, dependence, independence. We'll look at naive Bayes, then actually how you would go and implement it. Then we'll look at some tail bounds, how you use it, kernel density estimation, and then in the end exponential families. There's a fair chance that we will only get to the end of the tail bounds, maybe the beginning of kernel density estimation. And, well, you can read through the XKCD at some point, but it's, yeah. That's what you want to avoid. Green jelly beans and acne. Right. So we'll start with very basic probability theory, and I think I can pretty much skip over that. Everybody here knows it, I think. So, you know, you get the joint events. Right. Now, okay, this is where things get a little bit more interesting. So you might have, you know, dependent random variables or not so much. So like the login behavior of two users might be approximately independent, or disk crashes into different colos might be approximately independent. But in a lot of things, things are dependent, and that's actually a good thing, right? So this is an infamous example of dependence. You fired the bullet, you've pulled the trigger 5 times, and you're still alive. Well, you know exactly what's going to happen at the next time. So it's everywhere. Now, let's look at a very primitive graphical model. We want to spam classification, so we have spam. And whether it's spam or not, then I have a process which generates a mail. So then P of the joint distribution of spam and mail is, you know, P of spam times P of mail given spam. So this is the model of where somebody sits at a computer, decides, yeah, okay, I'm going to write a spam email, so he writes a spam email and sends it off. Of course, that's not quite true, but so the useful tool in this case is Bayes rule. So you can, who has not seen Bayes rule? Okay, no hand will go up, I know. It's embarrassing. This is possibly, this is possibly a nice and maybe slightly counterintuitive test if you've never done the numbers. It's worthwhile going through. So suppose I want to do an AIDS test, and let's say I'm in a fairly healthy country where only 0.1% of all people are infected, and suppose I had a test that detects all infections, but it also reports positive for 1% of all healthy people. And so I go to the doctor, and, well, he comes back with a very serious face and says, well, you know, the test reported back positive. Okay. What probability that I'm actually infected would you pick given this? Okay. Who picks 90%? Who picks 10%? Who picks 1%? Okay, and the rest is asleep. Okay, so let's just go through the numbers, because it's I mean, the first time you do it, it's kind of surprising. Not the second or third time, but people have gotten convicted for things like that, where the jury and the judge basically didn't understand statistics. So let's just, you know, do the following thing. So the probability for the test outcome, given that the person has AIDS, and the probability he has AIDS, divided by, in this case, I need to sum over the probability that he has AIDS and the probability for a particular test outcome if he doesn't have AIDS. So, well, by Bayes rule, this gives me exactly probability of AIDS given test. Okay, so we do this, right? And we get, you know, 9.1%. So, well, that's not very satisfactory. What can we do better? Well, we use a follow-up test, right? And that follow-up test, you know, has 90% positive for well, reports 90% of all infections, but 5% for all healthy people. And, you know, you get then about almost 36%. So here are 2 questions. First of all, why can't I just go and use test 1 a second time? Because after all, you know, test 1 is a lot better than test 2, right? Okay, yes?
The outcome is correlated. The second outcome.
Exactly.
Is correlated.
Exactly. You're absolutely right. So I was able to use that second test under the assumption, and that's already in the algebra here, that conditioned on the health status of the patient, the outcomes will be independent of each other for test 1 and test 2. So in other words, they are conditionally independent. So. And you may or may not have seen that as expressed. I think those of you who've taken Meister Martin's class would have, namely you will have that T1 is conditionally independent of T2 given the health status. So if I know this, I can treat those two as independent random variables. So this is something that we're going to use in naive Bayes. And the naive part in naive Bayes is that we will make exactly that assumption, but we're not going to use it only for 2 different AIDS tests, but we're going to use it for every single word in the vocabulary. Okay. Now, before moving on, here's an important and useful warning slide. Namely, logarithms are really a good thing if you're dealing with probabilities. And you might think, well, that's kind of obvious. Yes, it is obvious in hindsight. But your code may actually do horrible things otherwise. So here's what's going on. So one of the probably least exciting parts of numerical analysis, at least for me at the time when I took the class, was floating point representations of numbers, right? But it's actually important to know what's going on. And yeah, I've fallen into that trap too, so maybe if some of you avoid that code error, then it's good. So you basically store the actual numbers like 1.2593 whatever in what's called a mantissa, and then in the exponent you basically store the power of 10 that you're going to multiply it with. Then you have a sign. Now if you're multiplying probabilities, then all the real action is happening in the exponent, because you're going to move up and down orders of magnitude. So you're going to use these 11 bits to really carry a lot of the information, whereas these numbers here are probably going to play second fiddle. And that's very stupid, because you're going to run out of space here very quickly, and you're going to get numerical overflow or underflow. The overflow you usually realize because you somewhere get infinity. The underflow, if you're multiplying a lot of numbers that are less than 1, you may not notice, because you will get a 0. And then you will get 0 probabilities for things that actually otherwise would have non-zero probabilities. Or at some point you will get division by 0. Now you might say, well, hey, this is sort of obvious. Yeah, it is, except that if you go through some code, so at least a year ago in the Mahout-Dirichlet process clustering, they fell into that trap. They fell into a few other traps too, but that was one of the bugs that they had. They worked with probabilities. So what should you do instead? Well, the good thing is that whenever, so define pi to be the log of the probability, whenever I take products, it just becomes a sum. And whenever I'm taking sums, here's what I'm doing. I'm going to take the largest of the elements here, and I'm adding to that the log of the sum over the exponentials of the largest of whatever log I have here minus the largest. Okay. And you can convince yourself that this will give you the log of this expression. And the good thing is that now I don't get numerical over or underflow. The scale is automatically right by looking at the largest of those terms. And then everything in here is going to be negative, because I'm subtracting the maximum from it. So e to something negative is going to be less than 1. I'm summing over this. It's going to be fairly well behaved. If I get some numerical underflows here, well, that's not a big drama, because I've already pulled out the leading term. So keep that in mind if you go and implement something, and some of you might actually implement some probabilistic reasoning in this class. So remember that slide when you do it. Okay. Now let's look at something very simple, namely naive Bayes. So how does naive Bayes work? So the key assumption is that all those words occur independently of each other given the label of the document. So this is like, you know, maybe I have a monkey and a cat, and I randomly pick either a monkey or a cat, put it in front of a typewriter and let it write. And the character sequences will be different, and then you would assume that each of those symbols has been generated independently from each other. So, in other words, what I get is that P of all those words given spam, or not spam, is the product of P of Wi given spam. This is a modeling assumption, it's not true. Now the nice thing is that usually when people on Slashdot write about a Bayesian spam filter, they mean a naive Bayes spam filter. So it's not very Bayesian, but yeah. So it's just very naive. So spam classifier, in this case, would be, you know, you just use Bayes rules, so it's just P of spam given all the words, proportional to P of spam times the product P of Wi given spam. And so what do I need to do? Parameter estimation in that is actually very easy. I just go and compute the spam probability. So I go and compute P of spam here. And then for each word, I compute its distribution conditioned on spam or not spam. So here's a few examples, of course. You know, you can get a few of those phrases. And, well, this one unfortunately is just as likely. So, which tells you that maybe the naive Bayes filter is a little bit too naive. Nonetheless, it's quite popular and it's a good baseline, and the algorithm better beat it, otherwise it's not a good algorithm. So, let's have a look at the graphical model. So it's just, you know, spam, and then condition on that we get all the words. So, and then of course, since I'm lazy, I use plates. Who has not seen plates before? Okay, okay, that's good. So this is just a statistical for loop. And then of course the goal is how do you actually estimate this? Now of course, in a spam filter you have a lot more and different data. So you might have emails like the headers, the body, various metadata, labels. You know, assume that, you know, the users might actually label all the emails, which is of course not true. If they don't, then you look at how they behave and you can infer from that whether something might be spam. You might actually need something that's very high throughput, so you might want to process billions of emails, thousands of servers. But what you ultimately need to do is you need to estimate P of y and P of xi given y. So here is a closer approximation to what some of the data looks like. So somebody here wrote me an email, and well, that's where the actual email starts. This is all the junk that happens on top of the email. And these are useful things to extract features. So, for instance, in this case, it went from a Gmail account to my account, which is smaller.org, which is actually hosted at Gmail. So, from all this path, you can already figure out that maybe the recipient is somebody who has, you know, knows at least how to, you know, modify some DNS scripts. And the sender, well, basically, you know, you have the degree of reliability, for better or worse, that Gmail offers. Then you have a lot of other things like what time it was sent. So, for instance, if the email is sent during the day, then maybe there's a higher chance that it's actually a real email. On the other hand, if I get an email from somebody from this class at 4 a.m., well, maybe your account has been hacked or you're desperate getting your homework done. So, how do we actually implement this? So, I might have those thousands of faulty machines. That's our standard MapReduce setup. So, how are we going to do this? So, this was, you know, the word count that we had. Now, let's go for the naive Bayes classifier. And I'm going to make it really, really simple to make sure, you know, we get the basic idea across, and then, you know, you can easily think about how you can make it much better. So you have two classes, spam and ham, binary features, like whether the word is there or not. And the algorithm does something very simple. It just counts whether a particular feature occurs for ham or for spam, and they count the number of ham and spam emails. And then it's very easy, so I can just work out p of xi equals true, given y, well, I could just work that out by counting how many times a particular feature occurs, like computer science, divided by the total number of emails that are ham. And I would see that probably predominantly it occurs in ham emails rather than spam. And maybe for dollars, this would predominantly occur in spam. And then p of y is just a fraction of spam emails that I'm getting. Then, once I have that, I can just work out that product. Okay. Can anybody see a problem with this approach? Basically, this is not going to work. Any suggestions what could go horribly wrong? Yes?
If there's a word that never appear, or just a new word that I never,
Correct.
I got a zero that I didn't need.
Correct. Our naive Bayes classifier will be overconfident and unaware of it. So if I have a word that never occurs in spam or ham, well then my probabilities are undefined. Okay, well maybe I throw those words out. But if I have a word that just happened to be, that occurred maybe once, it occurred in a spam email, then this poor classifier is going to decide that each email that has this word occurring in it should be considered spam, which is of course wrong. Furthermore, it may even be that it has a word in it that occurred only with spam and one that occurred only with ham. And then I will get 0 as my probability estimates are normalized for ham and spam, and the entire thing falls over. So in other words, our probability estimation procedure is seriously bad. And I'll show you on the next few slides when we get to exponential families and so on, how you can actually fix this and get much better probability estimates. So with that aside, let's for the moment look at how we actually will go and implement this. So let's look at the simple sequential algorithm as we go through it. So for each document, so this is already set up such that we can average to MapReduce. We aggregate, the label counts, given one. So then for each of those features xi in x, in that document, we also aggregate the corresponding statistic for xi and y. So in other words, I might, if I have something fancier than a binary presence or absence filter, I might want to count how many times the word rich occurs, or how many times the word homework occurs, or how many times the word Viagra occurs, or whatever. And then I can use this to come up with an estimate of the distribution of, let's say, the word rich conditioned on the email being ham, and the same distribution conditioned on spam. Now then, I go and emit all those things, and for y, I can just easily go and estimate the distribution p of y. In a binary problem, this is trivial. It's just counts and ratios. Now, for x given y, I just need to get all the xi y pairs for a given y, and then I just do density estimation. And I could use whatever tool I want. I could use Gauss, Laplace, Poisson, mixture, anything that I want for this. That would give me a slightly less naive Bayes classifier. And then for a new instance, I just use my standard recipe. So how do we do that in MapReduce? It's already nicely color-coded. We basically go and have a mapper which takes each document one at a time. It emits the label. It emits the label and word count pairs. The reducer takes both the labels, so one of those reducers is going to take all the labels, the other one is going to take label and maybe the word dog, the other one label and the word maybe homework, and the third one label and the word 8, and you aggregate. And then in the end you can use these statistics to come up with that probability estimate. And this parallelizes quite nicely because I can essentially have all the documents being processed on separate machines, each subblock, and then afterwards the reducer just takes all the statistics for a given feature and aggregates it. So it's very, very basic, and I mean you can easily implement a poor version of that, and early versions of maybe Mozilla Thunderbird had one of those. So there wasn't much machine learning in there, but it's simple enough that an engineer can do it quickly. Any questions so far? Okay, so let's do something very simple again. Let's just estimate probabilities. So we have, binomial distribution, two outcomes, and here you can estimate the likelihood. And so P of x given the data is just that probability first count raised to the first count 1 minus that probability raised to the count that I get tails. And so then here's an inordinately complicated derivation, maximum likelihood estimation, for actually getting a distribution with those probabilities, and not very surprisingly, I get number of heads divided by number of heads plus tails, and for tails likewise. I'm not going to bore you with very much in detail. The one cool thing that we're going to use over and over and over later on is the fact that the empirical probability estimate, here this is the number of heads, the empirical estimate frequency, is the probability that you're going to pick. And so in maximum likelihood, for exponential families in general, you're going to design a distribution which has the property that the empirical averages match the expectations under that distribution. Now, of course, rather than binary, you can have discrete distributions, and you get the same thing. Now, these are probably pictures that you may or may not have seen. At least the first time you see them, it comes as a bit of a surprise. I didn't expect the deviations to be as large as they are. So here's what I did. I took Python and just, had it toss a dice 12, 24, 60, 120 times. And of course, you would expect that, you're going to see 2, 4, 10, and 20 occurrences of each number. Now, this is not what you're seeing, right? You're seeing fairly drastic deviations. And so the key question is, how can we get a handle on those deviations? Well, and this matters actually quite a bit. So, you care about it for computational advertising, you want to find out whether your website's working, and so I'm going to walk you through a few tail bounds and what they mean in terms of actually estimating those probabilities. So, here are some simple things. First of all, okay, we need expectations. Well, that's straightforward. Empirical averages are just, just sum over. I want to get the empirical average of some function and just sum of the things. So this is completely straightforward. Now, here's an example of the type of question you might want to answer. So a gambler rolls the dice 100 times, and the 6 only comes up 11 times. The fair number, of course, would be 16.7. So you want to know whether the dice is wrong, and so you can actually work out that sum. At least your computer can easily do that. That the probability that it will occur 11 times or less, and this is around 7%. So that tells us that things are probably okay. But what we would like to be able to do is get the general theory. So in practice, you care less about gamblers, but you care more about whether your new ad campaign is working, whether your page layout is better, or whether your drug is good. So you may have heard of A/B testing, and so these are essentially some of the precursors of what we're going to get into later on with active learning. So let's just look at how quickly things converge. And here's what I did: is I just had computer toss the dice maybe 1,000 times, and I took the average, and it should just converge to 3.5. And here you can see that it does converge with some effort. So the obvious things is, under which conditions does it converge. So the theory for that, the very basic one is, are the laws of large numbers, and then central limit theorem. We're actually going to prove those. So let's say we have a random variable, xi, means mu, and I take the empirical average, then the weak law tells me that, in the limit of infinite sample sizes, the probability that I have a deviation between my empirical average and the true mean, that this is greater than epsilon, is 1, for any epsilon greater than 0. The strong law tells me that this actually that the mean actually converges in probability. So that's a much stronger statement. Now, what I'm actually interested in is not just whether it converges, but actually how fast, because I care about it for maybe some service that I'm running. And so an explicit application would be, let's say I want to check whether my new web page ranking algorithm is better than the old one, right? So what I can do is I can have a data stream, and I run the old system and I run the new system, and I check how many clicks I get and maybe at which position or whatever other performance score I have. And ideally, I want to be able to tell as quickly as possible whether the new system is better. Well, why as quickly as possible? Because I want to show users as quickly as possible relevant content. At the other hand, I don't want to be just unlucky that I got a few questions that were very simple. And so there are all sorts of very clever interleaving tricks and so on, how I can make these results more meaningful, where it's more than just, you know, do the users like blue or black better. But this is sort of the precursor of some of these techniques. So the interesting thing is that, you know, if you look at the empirical average for a dice, it's the same curve as before. I've just drawn 5 samples. You can see it actually fits very nicely into this blue curve. And what we're after is how we get this blue curve. I can already tell you that much, that these upper and lower bounds are basically the square root of the variance of the random variable divided by sample size. And here's the central limit theorem. So basically I have independent random variables with some mean mu and standard deviation sigma I. So the random variable here, which is basically empirical average minus mean, divided by, here's the variance, but square root of that, so that gives me the right scale, converges to a normal distribution with zero mean and unit variance. So this means this random variable goes to 0 eventually, but it varies around 0 with, you know, if you factor the decreasing scale in with normal, with basically like a normal distribution. So if we have ID random variables and we take a simple average, it means that this quantity here is normally distributed. And that tells me the rate at which it converges. So in order to prove, so in other words, we get an order 1 over square root sample size convergence to the truth. This sounds quite innocuous, but it actually means that a lot of things are really hard in estimation. So they are fairly easy as long as you have, as long as you don't care about the high degree of accuracy. But as soon as you care about the very high degree of accuracy, things get very slow very quickly. Because you need 100 times as many instances in order to get a 10-fold improvement of your estimates. That doesn't sound like much, but it can actually be very expensive. And there are sometimes techniques how you can get around this, and rather than getting an order of 1 over square root sample size convergence, get an order 1 over n convergence. And these special cases are usually very famous. So let's prove those theorems. So for that we need a few tools. First one is Slutsky's theorem. Who has heard of that before? Okay, it's a fair amount, about half, maybe a bit less. So the point is actually very simple. Suppose I have 2 sequences of random variables, and xi has its limit some random variable x, and yi has its limit some constant c. And in this case, if I have some continuous function g of x and y, which is continuous at the point c, then the random variable g of xi, yi converges in probability to g of x and c. Yep.
Does it matter how x and y converge to their
So in order to get information about the rates, yes, you want to know how quickly they converge, but to just show that they converge, you just need to have the probability that they converge up. Yep.
Meaning do x and y converge in probability or almost surely?
They need to converge in probability as far as I know. Otherwise you wouldn't get that. Now, I'm not going to prove Slutsky's theorem, but I'm quickly going to show you how you use it for the delta method. So we'll need that for the central limit theorem. So suppose I have some random variable which converges, to b, and I'm assuming that, with suitable rescaling, so this could be like what you have with central limit theorem, it converges to a normal distribution. And furthermore, g is a continuously differentiable function for b at this point and around. So then the point is that g of xi inherits all the nice properties that x have. And so what you do is you basically study what happens. We posit that this is where it should converge to. We look at that series. Now I can, so that's the claim, that basically g of x minus g of b, suitably rescaled, is a normal distribution with same covariance matrix sigma, but then you color it by the gradient of g of b. That's basically all it does. So, or Jacobian if you have a multivariate expression. So the proof is fairly straightforward. What you do is you use the fact that g of xn minus g of b, if I expand it around g of b, is, well, just, that difference. Basically, xn minus b, the an remains as we have it. And now, because of Taylor's theorem, it tells me that this is exact for some psi n on the line between xn and b. Okay. And now we're exactly in the situation of Slutsky's theorem, where we have some function which depends on two random variables, namely this one psi n, which we know will go to b, and because the interval gets smaller and smaller, and this one which will converge to x, and so we're fine. So then this is how you can show that g of xi then becomes asymptotically normal. Okay, now let's actually prove what we wanted to prove. So what we need first of all is the Fourier transform. So everybody knows what the Fourier transform is, I suppose. So I'm just going to denote f of little f of omega being the forward transform, and f inverse being the backward transform. And we know that, well, that forward and backward transforms are inverses to each other, that they actually constitute isometries. In other words, Fourier transform inner products are the same as before. And the nice things are that, for instance, I can take derivatives of the function and they work out into products here. And furthermore, that if I convolve two functions, then the Fourier transform of the convolution is just the product of the Fourier transforms. So this is a rather useful property, and we're going to use that a lot now when we actually look at limits of distributions. So in statistics, the Fourier transform has its own name, does the same thing, but has a different name, so it's called the characteristic function. And what you basically have is that you call it phi sub x of omega, that's of this random variable here. It's just, actually in this case, it's the inverse Fourier transform p of x. Okay. So just bear in mind that there's an inverse Fourier transform here, but everything else is fine. Now the cool thing is that if I have a sum of two random variables, and this can be written as the convolution between the densities of the random variables if they exist. Well, why would that be the case? Well, if z is given by x plus y, then x must take on the value z minus y, and then I have a distribution over that, distribution over y, and since if I draw them independently, this is what I get as density for the sum, and I need to integrate out y. So it's just a convolution. Now the good thing is that in this case, for sums of random variables, and this is exactly what we were studying before, well, the characteristic function is just a product. And furthermore, it's a rather nice thing is that the characteristic function is unique. Now it turns out, and we will probably not have time to go through that in this class, maybe at the end, depends a little bit on how we have to do it in terms of time, you can perform the same type of transforms with a lot of other functions rather than the exponential. As a matter of fact, you can plug in pretty much any Mercer kernel. And if these Mercer kernels have certain properties, and actually the condition is that they have to be characteristic, and the name comes exactly from that characteristic function, you can get a unique mapping between a distribution and then points in Hilbert space. And this lets you do very interesting geometry with distributions in Hilbert space. Now this would be probably subject for a less scalable but more statistical machine learning class. So we may not get to that very much at the end of this class, but that's just a neat aside. So if you want to know more about that, have a look at some papers that Arthur Gritton wrote recently. And you can basically do a lot of message passing and graphical models, all by essentially performing basically operations in Hilbert space. So it's a fairly flexible tool. Anyway, now let's prove the weak law of large numbers. So I do require that the expectation exists. This is quite a strong requirement, but okay, let's assume that. So then, you know, I can just Taylor expand e to the I omega x. It's just, I can just do that. It's just 1 plus I w omega dot x plus then a higher order term. So therefore, the Fourier transform, which is just the expectation of this, is 1 plus I omega expectation of x plus something that's a higher order term. So we need to actually assume that we can bound this tail, which is typically with x. So in that case, if I have an average of a bunch of random variables, because I'm taking convolutions, I'm taking products here. And since I'm taking an average, well, this gets divided by m, the size of the sample, raised to the power of n. Now this looks awfully similar to what you would use to introduce an exponential. So this converges to, you know, something that looks like 1 plus, so it basically converges to e to the I omega mu, which is just, you know, the delta distribution at mu. And if I expand it, I can immediately see that the mean has to be mu, and so we have our claim. So that just shows us that, you know, if I sum a bunch of random variables, well, they'll converge to, you know, I mean. So note that those moments need not always exist, and probably the most infamous example is the Cauchy distribution. And so if you take an integral of that times x dx, you see it diverges. Right? So it's easy to show. And so you might actually wonder, you know, after all, you know, it's a symmetric distribution. Can't I just integrate from minus infinity to plus infinity, and then, you know, it's symmetric, so the mean has to be 0? Well, it's not well defined, because you can always play with the integral boundaries and get weird things. But that would be, I think, a measure theory class. And yeah. Good. Central limit theorem, you basically use the very same proof technique. So we already subtracted out the mean, so we need the second order term. For that, we assume that this one exists. So the mean is gone. So here we have the variance. Then we just subtract that. You know, we do the center, we rescale. Then after a little bit of algebra, you see that this is the expression that you get. And so these are again higher order terms, so they all disappear nicely. And this one here remains. So this thing gives us, you know, e to the minus 1 half omega squared, which is a Gaussian. And so we get since the Fourier transform of a Gaussian is a Gaussian, we know this is the normal distribution. Now, this is all very nice in theory. Let's have a quick look at what it happens in practice. So here's the central limit theorem. So what I've done is I've taken a uniformly distributed random variable between minus 1 and 1. And I convolve it with each. So we get the hat function. Here it's a, you know, piecewise quadratic, piecewise cubic, piecewise quartic. And, well, it doesn't look like much. It just decays more and gets smeared out. Now, if you actually rescale things exactly with the 1 over squared sample size that you would, you get something that starts looking awfully similar to a Gaussian. So it's already pretty good up here. I mean, the tails aren't that good yet, but up here it's already there. you can actually use the same argument to prove that the limit of a B-spline kernel will be a Gaussian RBF kernel. So remember that for later on when we do kernels, this will be essentially the argument that we use for the limit procedure.
Sorry, what does that mean?
Fun?
What does that mean?
Okay, so okay, so later on we will work with generalized linear functions in high-dimensional spaces. We will more specifically be working with functions in infinite dimensional spaces. Now, in order to work with them, we need special tools, and the tool that we will be using are, for instance, kernels. So, Hilbert-Schmidt kernels. These correspond to inner products in high-dimensional spaces. As if you've never seen this before, don't be worried, you will see it when we get there. But basically, those kernels, in order to show that they actually correspond to inner products, there are various ways of proving this. One way is to show that they are actually the convolution between some function in itself. And as a matter of fact, we will be using that type of functions as the basis of what we're going to convolve with itself. So these things are sometimes also called B-splines. And you can show that these, first of all, correspond to kernels for, in this case, odd orders. So the first, third, and so on order, because you can always, so say, take the square root of them in Fourier domain and be safe. And secondly, we can then see also very easily how they converge to a Gaussian kernel. Okay. Now, what I've shown you so far is just the essentially asymptotic theory of what happens in the large sample size limit. Quite often we'll need finite sample size bounds. As a matter of fact, we will need that over and over and over again in the next block when we do data streams. So we really need finite tail bounds. So here's the simplest one that you can get. And you've probably seen this thing before. So it's a Gauss-Markov inequality, but it's actually an extremely useful one. So I have some random variable x, and it has a mean mu. And I want to know what's the probability that x is greater than some epsilon. And it turns out that this is less equal than mu over epsilon. Now this looks utterly straightforward, and as a matter of fact it is. I mean, here's the proof, right? Probability that x is greater or equal than epsilon is the integral from epsilon to infinity of dp of x, which is less equal than x over epsilon dp of x. I'm assuming that epsilon is greater than 0 here. Okay. Now, since I know that, well, this is, okay, so first of all I can pull out epsilon. Now, I know that this is, of course, less equal than the integral starting from 0 to infinity, dp of x dp of x. But that's exactly the mean. Okay. That's the simplest inequality that you can get. But it actually can be used to then generate stronger ones. So the next one is the Chebyshev inequality. And again, it's a very straightforward thing. So you have some random variable x with mean mu and variance sigma squared. And I want to make sure that mu hat m, so my estimate, doesn't deviate from the mean, and that should be just a single bar, by more than epsilon. And this is, of course, less equal than, so that's the claim, sigma squared 1 over m at 1 over epsilon squared. Or, and this is where it gets more interesting, epsilon is less equal than the variance divided by square root sample size times that square of the failure probability. So up here we had epsilon goes like, let me write it down, because this is actually something fairly interesting what's going on. So here we have that epsilon has to be, is given by mu over delta. Right. Now, well, as a matter of fact, it's less equal than that. But now, for the Chebyshev inequality, we have epsilon is less equal than sigma over square root m times delta. So the interesting thing is that in the Gauss-Markov, we have a 1 over failure probability dependence. In the Chebyshev, we have a 1 over square root failure probability dependence. Yep.
What's the delta?
Delta is the failure probability. It's the probability that the inequality will not hold. So that can make a huge difference if you, let's say, care about, having a failure probability of 0.1. Then in one case, you will need basically 10 times as much data as in the other case. So this is where stuff gets interesting. And the question is actually, could you get something that depends logarithmically on that probability? And as a matter of fact, we can, and we will derive some bounds today and some more next week. So let's quickly prove this. So what you do is you basically take the following random variable y is x minus mu squared. Right?
The x is the
Pardon?
The x is the average.
Yes. Yeah, sorry, yeah, that's what it is. It's the average. So what you do is you use that as the new random variable. And you use it as the confidence epsilon squared. So then, of course, this has to hold. Because, that condition is the same if I square everything. I plug it into Gauss-Markov, and I get exactly the inequality out of it. So it's very straightforward. Yep?
On the top one, what if x is a Gaussian with mean 0?
So I don't have necessarily a Gaussian random variable, I just have some random variable with mean mu.
But what if it is? Then,
Well, if it's a Gaussian, then I can actually do much more clever things.
but then that doesn't hold.
No, it's
If
still...
it's mean 0?
Well, if it has mean 0, then, well, this is not well defined because I need a random variable that's greater or equal than 0.